Good evening. We are going to talk about limits and continuity in this lesson. So what we're looking at right here is we are looking at a function, and there's lots of different ways that you can think about this, and one of the ways is to think that if the function is a wavy wire, then it is continuous. Another way to think about it is if you can put your pencil down and go through the function, then it is also continuous. The term that we're going to look at is we're going to start talking about discontinuity. And that's what's happening right here. So you've got your two different types of functions here. Here we've got one where we can think of it as a wavy wire, and this is a continuous function, and this is a discontinuous or discontinuity. So this is a continuity and this is a discontinuity. Okay, so there's a couple of different things that we want to look at for this particular function here, the parts that make it continuous. So we've talked about approaching from the left and the right. So if we looked at this situation right here, and we would look at the limit of f of x, and we're going to look at it as x approaches c from the left, okay? And we are approaching this point right here. Okay, then we're also going to have the limit of f of x as x approaches c from the right. And then we are going to have f of c. So we've got three different things going on right here. We are looking for the limit of this function as it approaches from this direction. We're looking at the limit as it approaches from this direction, and we are looking at the value of the function at z. When all three of these things are equal to each other, then we have a continuous function. Okay, so this is a continuous function because the limit from the left, the limit from the right, and f of c are all equal. What we're looking at right here is called discontinuity or discontinuous function because they are not all equal. So here we've got our f of c. So our f of c value is what this point is right here. And then we have our limit of f of x as x approaches c from the left. And then we have the limit of f of x as x approaches c from the right. And as you can tell, right here is a different value than f of c and the limit as x approaches c from the left. Okay, so continuous and discontinuous. Now, we can have different types of discontinuity. Well, and this is the definition, I apologize. This is the definition, and this is what we just talked about right here. Continuity at a point. Assume that f of x is defined on an open interval, and we've got this value c. Then f is continuous if the limit as x approaches c equals f of c. Okay? And these are the three things that must happen for something to be continuous. Our f of c has to be defined, okay? Has to be defined. That means that there's a value there. The limit has to exist, and they're equal. So all of those things have to happen for something to be continuous. So let's look at some pictures. Let's look at some pictures right here, okay? The limit f of x as x approaches c exists, but neither the limit is not equal to f of c or f of c is not defined, then we say that f has a removable discontinuity. And so that's what's happening right here. Okay, and this would be a situation, or one example of this is when we have a rational expression and the numerator can be factored and the factor in the denominator can cancel out. That's what happens right here. We don't have an asymptote, we have a removable discontinuity. And that's what this picture is showing us, a removable discontinuity. This picture right here is showing us a continuous function. Okay, so we've got our limit as we approach from this direction, our limit as we approach from this direction, and the function is defined at 2. Here, that's removed. Okay, so let's look at an algebraic, and these are kind of your graphical ways to think about this, and I want us to look at our algebraic ways to look at this. So what I'm going to do right here is I've got to try and figure this out. Okay, I've got to see what this is. So this right here is a difference of a perfect cube. So we're going to factor this difference of perfect cube right here. Okay, so I've got the limit as x approaches 2 right here. I'm going to factor this, and I'm going to have x plus 2. It's x minus 2. Got to remember my factoring, x minus 2. And I'll just write this down right here. This is a difference of perfect cubes, a difference of perfect cubes. So that's going to be a cubed minus b cubed. And that factors to a minus b and a squared plus ab plus b squared. That's how that factors. So we just have to kind of go back and remember that factoring, okay? So our a value here is going to be x, and our b value here is going to be 2, and then we're just going to follow this formula right here. So we're factoring this difference of perfect cubes. So I have an x minus 2, and then I have x squared plus 2x plus 4. Okay, and then I've got my x minus 2. So all I did right here is I factored this numerator. I factored the numerator. So when I factor the numerator, I'm able to cancel this out right here. My x minus 2 both cancels. When that happens, when this happens algebraically, we end up in a situation that looks like this right here. And that's called a removable discontinuity. Because this is a rational expression and we cannot have 0 in the denominator, and when x equals 2 we get a 0 in the denominator right here, that is when we have a removable discontinuity. We don't have an asymptote right here. There's not a vertical asymptote right here because that cancels out. And I know you guys did a little bit of that in Math 112 where you have the hole in the graph. That's what we're looking at right here. We're looking at a hole in the graph, a hole in the graph. That makes it a removable discontinuity in this situation. Okay. So here is when we have a jump discontinuity. So we have removable discontinuity. Here we are talking about jump discontinuity. Okay, this occurs when one-sided limits exist, but they don't agree. They're not equal. Okay, so the limit of this would not agree. Okay, the limit of this would not exist because our right-handed limit and our left-handed limit does not exist. Okay, so in this one right here, this is what we call a jump discontinuity. So these are what we call piecewise functions. And I know that you have graphed piecewise functions in the past, and we're going to be looking at some piecewise functions for the rest of today's lesson as well. Now, I want to talk a little bit about right and left, the function being left continuous and right continuous. So I'm going to go to the next slide, and then I'm going to come back to this. So a function that is left continuous means that as the limit of f of x, as x approaches c from the left, that's where we equal f of c. Okay, so let's look at this right here. This one right here. My limit for this as x approaches 2. So the limit as x approaches 2 from the left is going to be the same as f of 2 in this picture right here. So this is left continuous. Left continuous. That's what this means right here, left continuous. Because this right here, we've got that solid dot. Okay? Now, a right continuous is if our function, if the limit of our function from the right is equal to f of c. And so in this situation right here, this would have to be an open circle if we were going to make this one right continuous. This would have to be an open circle, and this would have to be filled in. So that's how you determine your left continuous and your right continuous. In this picture right here, it's neither. We don't have left or right continuity here. So this is neither. It's neither right here. Okay, now let's remind ourselves a little bit about when we use our parentheses and when we use our brackets. Okay, so when I use a parentheses, that means the number is not included in that interval. Okay, not included in that interval. And when I use brackets, that means the number is included in that interval. Okay, and you can have a parenthesis and a bracket, or you could have both brackets. Okay, you could have both parentheses. You could have a bracket and then a parentheses. Okay, so lots of different ways that you can use it here. I want to remind you, anytime that you're using infinity or negative infinity, and I wrote that incorrectly, so that's going to be negative infinity, or let's try this one more time. There we go. Anytime I've got negative infinity or infinity, you're always going to be using your parentheses. You're not going to use your bracket at all for negative infinity, infinity. And so what this is saying right here is that we can talk about just an interval of that. So you can have a function that is continuous on the interval. And for something to be continuous on that interval, it's got to be continuous at every point on the interval. Okay, and so we can look at a function, and just like we can limit the domain, we're really limiting at what interval we're looking at on the function. So let's look at a piecewise function. Sometimes I think our piecewise functions make it a little bit easier for us to visualize. Okay, so let's talk about this for just a couple of minutes before we start looking at the different details of the graph. Okay, first thing I want you to remember is that because of this right here, this is called a jump discontinuity. So this is a jump discontinuity. Okay, now this would be right continuous at this point right here. So we're looking at this point right here. So if we were to look at x equals 1, we are looking at a situation where we're looking at a right continuous. And that is because if we were to look at f of 1, we would get 3. Okay. And if we were looking at the limit as x approaches 1 from the right of f of x, then we would also get 3. And because f of 1 equals 3, and the limit as x approaches 1 from the right of f of x also equals 3, that is why this is right continuous. Now, this part of the function right here is continuous on the interval -infinity to 1. And notice that this does not have a bracket right here because of this open circle. So it's continuous on this interval. Okay, it's continuous on this interval. Now this piecewise function right here is this graph. Okay, so this is how this graph is defined. So I just want to show you just a little bit. So what we're looking at is when we're looking at values that are less than 1, we follow this rule. And the rule that we're following right here is f of x or y equals x. And we are following the y equals x rule for this interval. And this interval that we're looking at right here is -infinity to 1. That's what this is telling us right here. Then our next part of this is telling us that from 1 to 3, we are going to follow the rule f of x equals 3. And you can think about that as y equals 3. And that is this part of the function right here. Okay, and let's go ahead and highlight this part of the function right here. Then once we're greater than 3, when we're greater than 3, we are going to follow the y equals x again. And this particular piecewise function just had the same rule in 2 different places. They don't always have that. You can have 3 different rules. Okay, and that is for that goes on from 3 to infinity. And so this is a piecewise function. This is an example of our jump discontinuity. And here we have a right continuous interval or part of the graph right here. Okay. So let's look at another one. So here, oh, it's actually our same graph. So at x equals 3, at x equals 3, okay, we have our function. So we're going to look at the limit of f of x as x approaches 3 from the right. Okay, so as x approaches 3 from the right, that's this direction right here, we are also approaching 3. Okay, then when we look at the limit of f of x as x approaches 3 from the left, okay, so that is from this direction right here, we are also approaching 3. And then we want to look at f of 3. Okay, and then f of 3 is also 3. Now, because this limit right here from the right and this limit right here from the left, because they agree, that means the limit exists. So we've got the limit as x approaches 3 of f of x, and that is 3. So that means we are continuous at x equals 3. Okay, we are continuous at x equals 3. Okay, so let's start talking about infinite discontinuity. So let's go to the next screen. We're going to talk about this. We say that f has an infinite discontinuity at x equals c if one or both of the one-sided limits are infinite. Okay, we say that f has an infinite discontinuity if one or both of the one-sided limits are infinite, even if f of x itself is not defined at x equals c. Like with a jump discontinuity, in this case, f is not continuous at c because the limit of f of x as x approaches c does not exist. Now, in this situation right here, we are able to find the limit. And the reason that we're able to find the limit in this situation here is because our limit of f of x as x approaches to is infinity. And that's going to be from the, let's talk about it from the left, okay? So if we're approaching 2 from the left, we are approaching positive infinity. Then if we are approaching 2 from the right, so the limit as x approaches 2 from the right is also infinity. Because these two agree, because these two situations right here agree, then our limit exists. Okay, so the limit of f of x as x approaches 2 is also infinity. Okay, but we still have an infinite discontinuity because we've got a vertical asymptote right here. So the limit exists here, okay, but we still have that infinite discontinuity. Now here, we have the infinite discontinuity here, but our limits don't agree. So in this situation right here, I've got the limit as x approaches 2 from the left, and let me write that a little bit easier for you to see. So I'm going to say the limit of f of x as x approaches 2 from the left, okay, that is going to be negative infinity. So the limit of f of x as x approaches 2 from the right is going to be positive infinity. These do not agree. We still have an infinite discontinuity here, and the limit as x approaches 2 of f of x does not exist, and that's because the two limits do not agree. Okay, and again, we've got that infinite discontinuity. Now, in this situation right here, we have a limit that isn't infinity coming from the left. So in this situation, our last one, we've got the limit of f of x as x approaches 2 from the left. That limit is 1, okay? And that is because in this direction, we are approaching 1 as we approach from the left. Now, the limit as f of x approaches 2 from the right is positive infinity. And so we still have this infinite discontinuity. We do not have a limit. The limit does not exist here because these two do not agree. Okay, so we have an infinite discontinuity. Our limit does not exist because they do not agree. Now we can look at the limit from the left and we can look at the limit from the right, but because they don't agree, we do not have a limit. So this is the limit of f of x as x approaches 2 does not exist. Okay, so we have our jump discontinuity, we have our infinite discontinuity, and then we have our removable discontinuity. Okay, so we have removable discontinuity, that's when we have our hole. Then we've got our jump discontinuity, and that's when we've got a jump in the graphs in our piecewise functions. And then we have infinite discontinuity when one or both of the limits approach infinity. Okay? Now, let's look at polynomial and rational functions, and this is related back to domain. So just think about our domain, and this would make sense. So if you look at this situation right here, our domain is just all real numbers, so we're good. Okay? Here we would have to limit our domain because of our denominator. And again, right here, we would be limiting our domain because of our denominator. Another time that you have to limit your domain is when you have a square root, or where we have a even root. We have to always limit our denominator when we have an even root. So if we're taking the 4th root or the 6th root or something like that. Okay, so what this is telling me is when I am looking at the domain, we can say that a function is continuous on its domain. Okay, so in this situation, our domain does not include positive and negative 1. Okay, but it's still continuous on its domain. That is what this is telling us right here. It's continuous on its domain. So we're looking at it's continuous on all values okay, so it's continuous everywhere except when x is not positive or negative 1. Okay, so this is very much related to domain. And the same is true for our second problem right here. This is continuous on our domain, and the only place that it's not going to be continuous is at x equals 0. It's not continuous at x equals 0, just like this one is not continuous at plus or minus 1. Okay, so here is some basic functions that we'll be looking at, and we'll be able to look at the continuity for these. So this right here is 1 over n. 1 over n, okay? So one of the things that we do in calculus is we use a lot of rational exponents. So I just want you to remember what a rational exponent is. So if I've got x to the 1 over 3, okay, what that means is x to the first power, and then I am taking the cubed root of that. Okay, so then let's say if I've got x to the 3/4, what that means is I've got x cubed, and then I am taking the 4th root of that. So very often when you've got radicals, and you are going to take that radical and you're going to turn it into a rational power, and that's what we're doing right here. That's what this function is what we're talking about. So here we've got continuity on some basic functions. X to the 1 over n is continuous on its domain. Continuous on its domain. So let's look right here. This is y equals x to the 1/2. Y equals x to the 1/2 means y equals the square root of x. Okay, so that's x to the first, and then this right here is square. Our index right there for this, the radical is 2. So that's the square root. X to the 1/2, that means the square root of x. And that's something that you want to be able to go back and forth with pretty quickly. It's a rational exponent right here. Okay, now we know that anytime we've got an even index or an even number down here, we cannot have any negative numbers inside that radical. Okay, because we're no longer in the real category of numbers. Okay, so if you were to graph y equals the square root of x, this is the graph that we would look at right here. So this is continuous on its domain. That's the key word right there. That's continuous on its domain. Here we've got x to the 1/3. x to the 1/3. So that's going to be the cubed root. So that's y equals the cubed root of x. Okay, and that's all real numbers. So this is continuous on the whole number line because the domain for this is all real numbers. The domain for this is only positive numbers, so it would be 0 to infinity. Now you can have 0, so we would have a bracket around 0 because you can take the square root of 0. It's just 0. But here I can take the cubed root of negative numbers. So our domain here is all real, negative infinity to infinity. So that's why the function is going on our negative values because it's all real numbers. Now, many of you just got out of trig and say this is a partial graph of sine of x. And then we've also got cosine of x, and those are continuous on all real numbers. So if you think back to the domain, you always want to think back to the domain. Okay, here's some exponential functions. Exponential functions are continuous from negative infinity to infinity on the real number line. Log, you've got to think back to your domain again. Okay, so for log functions are the inverse of trig functions, and their graph is going to look like this. And so you're going to be looking at your positive numbers there for your logs. So domain and continuity, you really want to think about those two things with your domain and the relationship between domain and continuity. Okay, let's look at a little bit more trig. So we're going to look at the continuity for tangent of x. So I know many of you just got out of trig. So we've got the tangent of x, and when we remember, tangent of x is sine of x over cosine of x. Sine of x over cosine of x. So the domain of tangent of x is undefined anytime that cosine of x is equal to 0. And I'm not talking about x being 0. I'm talking about the cosine of x being 0 because our denominator cannot be 0. Okay? So here we are looking at all of the values where our denominator is not 0. And so those we talk about plus or minus pi over 2, plus or minus 3 pi over 2. This is where the tangent function is undefined. And so at each one of these, okay, at pi over 2, 3 pi over 2, negative pi over 2, we have an infinite discontinuity at those points. Okay, infinite discontinuity. So think back to where cosine of x is undefined, or where, I'm sorry, not undefined, where cosine of x is 0, and that's where tangent is undefined. Okay, and then think back to your 112 where we're talking about inverse functions. Okay, inverse functions. So just a reminder, with your inverse functions, if I've got f of x equals x cubed, okay, the inverse function of that is going to be the cubed root of x. Okay, so those are your inverse functions. And that's a pretty simple inverse function. I know you've done much more complex inverse functions. Okay, so if f is continuous on an interval with the range, then f inverse exists and f inverse is continuous. Okay, that's just because if you remember, if I've got my domain of f of x is going to be the range of f inverse of x. Okay? It's a definition of inverse functions. And then the domain of f inverse of x is the range of f of x. Okay, that's just the definition of inverse functions. So if the range of f of x is continuous, then the domain of f inverse is continuous. Okay? And remember, f inverse is a reflection of the graph of f through the line y equals x. Okay? So that's just a little bit of a reminder about how your inverse functions work. Okay, and so again, we're talking a lot about concepts here and the definition of continuity, and really what we want to start doing is using substitution, and this is really where you're going to spend a lot of your time is evaluating limits. And in your next lesson 2.5, we really use algebra to find indeterminate forms. And so this process, the substitution method, this is where we are able to find our limits just by plugging in what we're looking for. So this works when this value is defined. So as long as what we're looking for, as x approaches pi over 3, as long as pi over 3 can be plugged into x, and we can determine what the sign of pi over 3 is, then we are able to find that limit just by plugging it in. Okay? And sometimes we want to make limits more difficult than they are because we forget that unless this is undefined, we can just plug it in. And you started doing that, and you're going to do a lot more of that over time. So in order to find the limit as x approaches pi over 3, we're just going to plug in pi over 3. Okay? And when we plug in pi over 3, we get square root of 3 over 2. So all I did right there is I found the sign of pi over 3. Okay? And we are able to do that because the function is defined at pi over 3. Okay? So I'm going to write this right here. Sine of x is defined at pi over 3. So we plug in to find value. Okay? Now, in 2.5, in indeterminate forms, we're going to do a lot of manipulating and doing some different parts of algebra to work out how to get a defined value. But right now, all we need to do is plug in. Okay? So this one right here, the limit as x approaches -1. We're in good shape right here because -1 is a defined value. Plugging -1 into the numerator and plugging -1 into the denominator doesn't make this undefined. So all I need to do here is use this method, the substitution method, and we're going to plug this in. So what's going to happen then is I'm going to get 3 to the -1 power. We are going to have to talk about what that means. And then we're going to plug it in the denominator, and we're going to get -1 plus 5 in the denominator. Now, I'm going to 3 to the -1. Now, this is in the numerator. 3 to the -1 means 1 over 3. Okay, and then I'm going to have -1 plus 5. So that's 4 right there. -1 plus 5 is 4. So I'm going to have the square root of 4, and that's going to be 2. Think about that as 2 over 1. So then I've got 1/3 divided by 2 over 1. Okay, that's the same thing as 1/3 times 1/2, and that's going to give me 1/6. So that is my limit right there. So the final answer to this right here is 1/6. Okay, and you are going to be doing lots more algebra, and we'll work through more algebra as we move into indeterminate forms.